Welcome everyone to IMSE881 Linear Programming lecture number 10. And today we're going to start talking about interior point method. So far in the semester, we're talking about only the simplex method. And we all know the simplex method actually work from corner point, which is extreme point, to extreme point until we reach to the optimal solution. However, the concept of the interior point is a little bit different. Instead of going through the extreme point and roll over to another adjacent extreme point at each iteration, and people thinking about, can we just go strictly through the interior of the feasible region and go straight to the optimal corner point? Based on this concept, there are three categories of algorithm we're going to introduce this semester. And the first algorithm is the Primal Affine scaling algorithm. And the second one will be the dual affine scaling algorithm. And the third algorithm is called Primal and dual affine scaling algorithm, which frequently referred as a path following algorithm. This lecture 10, we're going to focus on talking about primal affine scaling algorithm in here. Okay. First, we'll look at the standard form of a linear programming model and as a feasible region. Linear programming model P1 is minimizing C transpose times X and subject to AX equal to B and X is non-negative. And we can define the feasible region of P1 equals to P, capital P, equals to the set of X satisfying AX equal to B, and X is non-negative. But since we're going to try to keep our solution at each iteration instead of on the corner point, we're going to try to keep the current solution into so-called in the relative interior of this feasible region, which means the x is greater than 0 instead of greater than or equal to 0. So the question is all the x's will have a positive value. Instead of in the simplex method, we will keep only the basic variable has a positive value, and all the non-basic variable has a value of 0. And this algorithm will try to keep everybody positive in that case. And we call these regions called the relative interior of my feasible region. Next, we're going to look at the affine scaling transformation. We define a current solution at iteration k, x sub k belongs to n-dimensional Euclidean space, and all the x's are greater than 0, positive, for all the I from 1 to n. So therefore, xk belongs to the relative interior of Rn plus, which is the non-negative portion of Euclidean space. So we're using Ri of something to denote the relative interior of Rn plus, which is a non-negative quadrants of Euclidean space, n-dimensional Euclidean space, and define an n by n matrix. We'll call it capital Xk sub k equals to, and has its diagonal equals to each one of the elements from xk. Okay, and the off diagonal are all 0. And this is a non-singular matrix, since all the diagonal elements are strictly positive in this case, and also the xk inverse exists, or simply is 1 over each one, a reciprocal of each one of the diagonal element. So it's 1 divided by xik will be the inverse. So we define these so-called very simple affine scaling method, and we call the y. After transform, we change a variable from xk to y. And we define a functional transformation called t sub k and of xk equals to xk inverse times xk. It basically has a whole column of 1 instead. So we call it E column. E column is a vector with all the elements are equal to 1. So this is a very simple defined so-called affine transformation. What is this affine scaling transformation does? Here's the illustration. For example, here I have a feasible region in the original space before transformation. We call the AX equal to B. And we have a point right here, the blue point right here. We call the X sub K. It's the current solution at the iteration K, the current solution. And what we notice that this current solution is already very close to the boundary of the feasible region, which is the extreme point, as one of the extreme point. But the spirit of the interior point, we want to keep the current solution within the relative interior of the feasible region. So people start thinking about using a so-called affine transformation. Basically, if you have a spotlight over here and you're trying to project the current solution close to a corner point and map it into the more interior, relative interiors of another space, we call it AK times Y equals to B. And this new solution location, we call it YK, is in has a fair distance to each part of the boundary or the corner point. So this will help us to improve the so-called numerical calculation error for during the process. And this we refer as affine transformation. Basically, is projecting transform the current solution space, which is the feasible region, into another transformed space. And with the transformation we have defined, the y always is in the 1, 1, 1, 1 type of coordinate. So each iteration will perform this transformation, and we have a more numerical stability. However, with the concept of this affine transformation, we want to see at each iteration, we can easily transfer back from YK back to XK. Okay, even though we calculate the improvement at the next solution based on the Y, however, every iteration, I want to be able to convert it back easily to XK. So that's why we're choosing a affine transformation is easily transform forward. Inverse transform is also very easy to calculate. So the concept of this simple affine transformation is simply using the current solution and put it in the diagonal space and using its 1 over the diagonal space as its inverse. So we can easily transform from Y to X, also from X to Y in that sense. So this is a choice of transformation, which is easily transformed backward and forward. And that's the whole spirit for this particular version of affine transformation. Of course, there are more sophisticated transformation in other algorithms, but numerical results show this transformation is more understandable and it's tractable and it's easily to calculate back and forth. So that's a popular choice for solving linear programming problem. Let's look at some of the property for this transformation T. T is a well-defined map from Rn plus to Rn plus. So a transform from the positive quadrant of n-dimensional Euclidean space to the n-dimensional Euclidean space in the non-negative quadrant. And also, every single iteration the result of the transformation is always 1, 1, 1, 1, 1. It's a vector over 1. Number 3. This transformation is vertex if the currently xk is vertex, and then the after transformation, and that particular point is also a vertex, which is extreme point. If the current, number 4, if the current xk is an interior point, and after transform, the yk is also an interior point. So this is a well-defined transformation. Okay. So if x is a boundary of Rn plus, and transform after transform xk, tk of xk is also a boundary point. So tk is a 1-to-1 and onto mapping with the inverse transform tk inverse very simply can be calculated. It's just simply take xk times y, it will revert back to xk. Okay, so these are the 6 very well-defined properties for this affine transformation, and we can easily use to developing a algorithm based on this transformation. Okay, so now we start talking about the affine scaling algorithm, primal affine scaling algorithm. Given the current P1, we try to convert it into P12, actually equals to minimize of a ck transpose times y, where y is transformed xk, okay? And also subject to ak times y equals to b, and y is non-negative, where ck over here is actually xk times c, and ak over here is actually a times xk. Okay, so we can transform the original x problem from x and this decision variable to x and to y instead, using the current solution xk. The basic idea is the 3-step only, very simple. First, part A is finding an improved direction d such that, okay, and follow the positive step of this direction dy actually lead to a lower objective function value. So the new ck transpose times yk plus 1, this is yk plus 1, is always strictly less than ck transpose times the yk currently, for any alpha k which is a step size is greater than 0. In that case, we can conclude a times xk times dy is equal to 0 because it has to be a feasible direction. So the dy, the first here, guarantee it is an improved direction, and the second equation guarantee is a feasible direction, which means it satisfies ak times y equals to b. Okay? All right. Second, we're going to find a proper step size, step towards the dyk, and that means now the new yk plus 1 equals to yk plus alpha k times dyk is strictly greater than 0 still. That means it's still in the relative interior of the feasible region, which is still strictly positive. Then we're using this to update yk plus 1 equals to yk plus alpha k times dyk. And also, since we can calculate yk plus 1, we can easily inverse transform back to calculate the current solution of x. So the concept and the basic idea is very simple, and the calculation involves some kind of several matrix calculation. But we can also using the symbolic calculation to pre-calculate the symbolic computation and come up with a very easy steps and to perform this algorithm. Let's look at the next. We'll start talking about the detail for each one of the steps, part A is trying to find an improving and feasible direction. First, since we are minimizing the CK transpose times Y, and basically the inverse of a CK is then the best improving direction. And if the the direction has to be feasible, then the AK times dyk has to be equals to 0. So one of the methods to do is we can project, okay, the CK, which is my objective vector, CK, which is equal to C times X, capital XK, can project the CK onto a null space over AK to define a D. So this orthogonal projection matrix, we're going to see the geometric illustration next slide, equals to the PK. P sub k is the projection matrix, equals to I matrix minus AK transpose times AK times AK transpose inverse times AK. So this is a standard projection matrix, and we can convert it back to the original AK equals to XK times A transpose, and the AK times AK transpose equals to A times XK squared times A transpose. And the A is now the original constraint, inverse times A times XK. Several property is nice property for this projection matrix is PK equals to PK squared. Means if I project if we look at the let's look at the next slide first, and then we'll come back to talk about these property. The concept of this projection is the negative CK is actually the best solution, best improving direction I can find, but the negative CK may not be feasible because it's not satisfying AK times Y equals to B. So one of the methods what we do is taking the negative CK and project them onto this null space of AK transpose times AK times Y equals to B, which is the dyk. We define it right here. So this red point is current solution yk, and after following the direction of the dyk, and we can reach a new data point, new yk plus 1, and following this. So this is a basic concept. You can see that. First, let's look at the, the first property in the previous slide. And why is PK equal to PK squared? Geometrically, you can see that very simple. If I project this negative CK onto the null space over AK times Y equals to B, after the first transformation, the dyk is already on that null space. If I project one more time, it's still going to be itself. So it doesn't matter how many times you perform the projection, and the first projection is already represented on the null space. So I project one more time, or two more time, or three more time, doesn't matter. Second, PK equals to PK transpose. So PK is a symmetric matrix. Okay? So also, PK times C equal to 1 minus PK times B, and they actually equal to 0. So that means, in the next slide, you can see that PK times C, which is this dyk, is perpendicular to the red dotted line right here. Is 1 minus PK, okay? And these two vectors are perpendicular to each other, since this is a projection, orthogonal projection. So the two vectors multiplied together in a product has to be equal to 0 in that case. Okay? And many times I minus PK transpose B is equal, we call it error vector. This is a well-known property in the linear regression as well. Okay, so after this, we can actually define our improving direction, which is also feasible, since it's satisfying. Okay, AK times dyk equals to 0. Okay, AK times dyk equal to 0. So the dyk equals to projection matrix K multiplied by negative ck, which is project negative ck onto the Noeth space of ak times y equals to b. So we can calculate this a little bit, fairly simple. The ck equal to xk times c, so pretty much I can calculate that way. Okay. And this is the illustration why I can project negative cyk onto a Noeth space of ak times yk equals to b and producing this dyk.